Hello, and welcome to another lecture in the course. So today we're going to talk about the logarithm, what we want the logarithm to be, one of the most important functions in complex analysis, which is not actually a function, or it's a function if you expand your horizons about what functions can be. All right. So this is so we're starting chapter 4, so looking at subsection 4.1.1. All right, so let's start with some motivation. So let's consider z to the n. We said a couple of times. Basically, if you figure out how to handle z to the n, you figure out how to handle holomorphic functions locally. So let's look at z to the n. What's the primitive of z to the n? What's the antiderivative? Well, as long as n is not equal to -1, just, basic calculus says that's what it is, right? That's what we teach our calculus students. And, well, we teach them correctly. That is what it is. So it's really simple, right? Okay, maybe it's not defined at the origin if n plus 1 is negative, so if it's really going to be 1 over some power of z, right? So, okay. But, then the end probably wasn't defined in the first place there either, right? So, as long as n is not equal to -1, we have a nice formula for the antiderivative. So what about if n is -1, right? So what is the antiderivative then, right? Well, it's the logarithm, right? That's what we teach our calculus students. All right, it's a little bit more complicated in complex analysis. So let's get at least sort of a partial, in the end it's going to be an unsatisfactory answer. But let's start with the slit plane. So what is the slit plane? It's the complex plane minus the negative real axis. So maybe let me draw that over here. So if we have if you put the origin over here, right, in your in your plane, then you remove everything from the origin, everything negative, right? And so you have this this thing left, which is star-shaped, right? So it's everything minus the slit going off to infinity, right? It goes off over here to infinity, right? So that is star-shaped, or star-like, star-shaped, star-like. I think I'm using star-like in the book. So it's so we have that holomorphic functions have primitives here, right? So basically just by writing down a formula for them, right? Starting with the point where is with respect to which it is star-shaped, and taking a path integral along a straight line, that will give you a primitive, right? So that's what we proved before. So, including, maybe I should move to the highlighter again, including this this guy over here, right? 1 over z. So we have our logarithm, right? That's what we want to be the logarithm. Okay, so to antiderivative, well, there's lots of antiderivatives. So let's make it equal to 0 when z is 1, right? Just so that we pick one of them, right? And we're really, it's really star-shaped with respect to z equals 1. You can prove that. So you could just define it even with the formula there if you wanted to, right? But we have a logarithm there, and we call this the principal branch of the logarithm, the one that's 0. So capital log of 0. Oh, sorry, capital log of 1 should be 0, right? Okay, now what we want to show is that this capital log of z actually has this formula, right? where the argument, that's the principal branch of the argument, right? That's the argument that gives us values between minus pi and pi. All right. So what do we want to do? Well, let's define a new function that we want to show that is equal to the log, right? Let's call it L, right? And we're going to show that this equals the antiderivative that has the right value at z equals 1, right? So we just define this function. We don't know if it's equal to the log. We want to show that it's equal to the log, right, to the principal branch. All right, so first, what is it at 1? And you just plug in, right? You plug in 1 over here. So here, the logarithm, that's just the real logarithm over here, right? And so we plug in 1 modulus of 1 is 1, log of 1 is 0. The argument of 1 is the principal branch of the argument is 0, right? It's the argument between minus pi and pi of 1. That's real, right? So, all right, and positive. So, right, so we get 0, which is exactly what capital log at 1 is. So, all right, so it agrees at 1 point. Okay, we need to get all the other points as well. Right, so let's first figure out that it's holomorphic, and to figure out that it's holomorphic, we figure out that it's the inverse of the exponential, right? So if we take the exponent of L of z, then, well, you just plug in this formula, right? And we're only evaluating this on the slit plane, of course. So you plug in this formula, right? And this bit just becomes the mod of z, right? That's the real log, and I'm taking the exponential of a real number. That's just the real log, real exponential. That's the mod of z, right? So mod of z times e to the I argument of z. Well, that's basically the definition of what the modulus and the argument of z are, right? So this is z. All right, so L is the inverse of the exponential, at least on this, if we're restricting here, all right? So L is holomorphic, right? I mean, being holomorphic is a local thing. Locally, this is the inverse, right? I mean, the exponential is not one-to-one, of course, right? But it's locally one-to-one, right? So it does have local inverse. That's what it is, right? And we know by the inverse function theorem that inverses of holomorphic functions, if they exist, are holomorphic. And that's just a local thing. I just need to do it in any small neighborhood, right? Anyway, so that's just inverse function theorem gives us that L is holomorphic, right? I mean, a priori, we didn't know. I mean, we gave some weird formula, right? I mean, how do I know it's holomorphic, right? You have to somehow argue why that's holomorphic. All right, so let's differentiate this equation, right? I mean, among other things, we've shown this, right? So we didn't do it just to show that it's holomorphic, but let's use it again, right? Let's differentiate this, right? I mean, it's an equality, right? On U, right? It's where we're interested in. So the derivative of z is 1. The derivative of the right-hand side is this guy over here, right? And, well, let's use this formula again. E to the L of z is just z, right? So we have that L prime of z is 1 over z. It's the antiderivative, right? Well, it's an antiderivative, and we already know that it's 0 at z equals 1. So it's the antiderivative that we're looking for. It is the principal branch of the logarithm, right? Okay. We don't quite have the logarithm, right? I mean, it's the principal branch of the logarithm. which, just as we said about the argument, it's not actually as useful as you think, or as one would hope. But it's it is one of the logarithms, right? And if you use a different branch of the argument in a different domain, maybe, or even in the same domain, basically use a different range of the arguments that you're looking at, you just get another antiderivative of 1 over z. You get another branch of the logarithm. All right. Now, we want the logarithm, the one true logarithm, right? If I say the logarithm, the thing that we're going to define was a small l, right? Not the cap. Here it's sort of opposite. The capital L is the unimportant one. The little l is the is the really important one. The little log, right? That's the one that does everything that we want. So, hey, I mean, we have this nice formula for the principal branch, and here the argument is the principal branch. Let's just take the argument, the little a argument, and put it down here, and let's define our logarithm basically with the same formula, right? That's our logarithm. That's the definition of logarithm. It sounds a little crazy, right? I mean, it looks wrong for a number of reasons, right? It's the right thing, but it looks wrong. So first, it looks like a circular definition at first, right? I mean, on the right-hand side over here, this log is the real log. It's only applied to real numbers. It's it is the standard log. That's not this log, even though it looks exactly the same, right? This is a bit of an abusive notation. I mean, really, there should be a different notation for the real log, the thing with the domain being just the positive numbers. But yeah, there's never really any problem coming out of this, right? It's easy to distinguish which one we're looking at. And if it's hard to distinguish, you need to make it explicit, right? If somewhere in a proof or in text you're using little log and it's not clear which one you're using, you'd better explicitly state what is that. But generally, confusion doesn't actually arise. So it's not a big problem for using the same notation, right? So it's not really a circular definition, right? This is this thing over here is a different function. It's the real log. It's the log on positive reals, right? So that's one thing. But the other thing, it's not a function, right? This log is not a function. This guy is. This guy has exactly one value. It is the real log, right? This guy has infinitely many values. So this is it is actually also a different thing, right? Because if I plug in a positive real into little log, I have to think, well, am I using the complex log, or am I using the real log? If I'm using the real log, I get a single value. If I'm using the complex log, well, I'm gonna get all these values coming out of all the arguments, right? I mean, there's infinitely many arguments. I can always add 2 pi I or subtract 2 pi I or add 4 pi I or whatever and get another log, right? It'll be the same, it should be the same number, right? It's if I exponentiate it, right? So it's so I get infinitely many values here on the left-hand side. Even if I plug in some positive real, right? So okay, so that might be a little confusing sometimes, but here the second problem is that it's not a function. We are trying to define a function, but we didn't get a function. we have a multivalued function, which complex analysts are perfectly fine with multivalued functions. Just don't go on the internet and ask somewhere about multivalued function, because there's going to be some smart aleck somewhere that says, oh, no, functions by definition have only one value, right? Yeah, not for complex analysis. For complex analysis, yeah, multivalued function, that's fine. It's not a function, it's a multivalued function. Yeah, we're totally fine with that. No worries. All right, so here is the graph. And from the graph, you can actually see kind of the problem. It's not a complete graph, right? It's I've not only cut it, that I'm only showing maybe above the, above some disk, right? And so this is the real part, and this is the imaginary part, right? Because, well, it's hard to graph complex values, but also another thing that you notice here is that the real part is a nice function, right? The real part is just the log of mod z, the real log of mod z. That's a nice function. So it looks like this, right? It's this cone thing. It sort of goes to negative infinity out here as you approach 0, but yeah, it's a nice function, right? Singularity at 0, but yeah, otherwise perfectly good function. On the other hand, the imaginary part, yeah, it has infinitely many values, right? So above each, if I'm thinking of it as a graph above the z-plane here, as here, right? Then for each z, I have infinitely many points. Then there's going to be, if I keep following this, I'm going to get another, value here, and another value, and another value, and so on, right? And the same thing down here. I'm going to get infinitely many values, right? It's actually, one thing that I should mention. This is a little bit squished, maybe. Normally, if this would be something like when I drew it, this was the, this dark thing is the really the unit circle, and if this distance is 1, well, this distance should be 2 pi. It's not. I've squished it so that it fits on the picture, right? But that's what it looks like, right? All right. So, and as I said, if we travel around the unit circle here, right? And I'm going from z equals 1. So, over here, this is the positive real axis, this is the positive imaginary axis. So if I'm going around the unit circle, right? Well, around the unit circle, that's where mod z is 1. Mod z is 1. So log of mod z, log of 1 is 0, right? So this dark circle here, right? That's actually intersecting the z-plane. All right. Now, on this side, well, here it's a graph, so if I go around, I come back to the same thing. On here, I go around, I actually come back to a different point. That's going to be important in just a moment. All right, and as I said, real part is a nice function, right? That's just the normal log. The imaginary part, yeah, that has infinitely many values. That's the part that makes it not quite a function. It makes it a multi-valued function. The infinitely many valued function, right? But this is the correct definition. This is what we want the log to be, right? That's the logarithm. It's not a function, but it's the right definition of the logarithm. All right. So how do we use logarithm? Well, it's an antiderivative. We use it to compute integrals, right? So let's compute an integral of 1 over z. So let's parameterize the disk, right? So I'm going to start at z equals 1. Maybe let's not use the highlighter, right? So I'm going to start at z equals 1. I'm going to go around the unit disk in this direction, and I'm going to integrate 1 over z, right? And we're going to use the fundamental term of calculus to compute this, right? Because we have an antiderivative, log, right? Now, if we don't want to use the principal branch, or not without a bit more work, because it's not defined on the entire circle, right? The principal branch is not defined on the, on here, right? It's, in particular, it's not defined at this point, right? So let's compute it. Let's plug in our antiderivative, the real log, the thing that's defined everywhere, except z equals 0, of course. It's not defined at the origin. I mean, everything, the real part blows up and the argument is just not defined. Okay, well, the origin, bad, but everywhere else, fine. So it's log of 1 minus log of 1. So what is log of 1 minus log of 1? It's 2 pi I, obviously. Okay, maybe that doesn't sound so obvious. That seems like nonsense, right? I mean, I've subtracted log of 1 from log of 1, and I got something that's not 0. Well, that's because, I don't have the highlighter on. Well, because these things are not numbers, right? So let's make it a little better. Let's fix this. So how about if I add little quotation marks around it. That makes it better, right? I mean, this thing is a number, right? So it can't quite equal something where I'm doing non-number stuff, right? So over here, this is something, whatever that is. It's a multivariate function evaluated at a point minus a multivariate function evaluated at a point, whatever the hell that means. So I don't want an equality, but equality in quotation marks, right? And then this is a number, right? And okay, so we haven't really fixed it. But it's the right idea. So how does it work? It works by following a branch. So it's not quite maybe this, right? But it's the idea of doing this. It is taking one value of the logarithm and subtracting it from another value of the logarithm, and you have to figure out which values, right? And you can really pick an arbitrary one at the start, but then you have to pick the right one corresponding to that starting one at the end, right? So how does this work? So let's look at the graph. That's going to make it clear. We are integrating along the unit circle, right? So the values, the real parts, right? Look, the 1 over z, right? We're not integrating log, sorry. So the 1 over z, that's what we're integrating, right? But we're looking at what happens to the antiderivative, to log of z. So the real parts, well, they stay at 0 and end up back at 0, right? Some good. So I'm subtracting the same number from itself. So on the real part, it is 0. On the imaginary part, well, I start here. So let's maybe pick the log of 1 at the start of my path, right? I'm going around the circle. So at z equals 1, I'm going to pick it to be 1. And I now keep following this path, and here I pass under it here and follow it. And then I read off the new value at z equals 1, right? So now I have two values at z equals 1. One of them is 0, and one of them is 2 pi I, right? So it's 2 pi I minus 0, which is 2 pi I, right? So that's how we use the logarithm when we're integrating, right? Or at least sort of intuitively, that's what's happening, right? That's how the application of the of the fundamental theorem of calculus would work if we were using the logarithm, right? The logarithm, not just the principal branch, just the logarithm, right? So start with the log at 1, right? And follow until the end where we get 2 pi I, subtract, and we get what we want. All right, so a branch of a logarithm in some set U, here it can be any open set, is, well, some antiderivative that equals one of the values, right? We want it to be a branch of the log, right? So it has to equal, it can't be just any antiderivative of 1 over z, because you could, there's too many of those. You can add any constant, right? So we want it to have one of these. There's only countably many values that the logarithm can take, right, at any point. So a branch of the logarithm is an antiderivative of 1 over z that takes on one of the values of little log of 0, right? And it's, of course, it should be holomorphic. It's an antiderivative of 1 over z, right? Right, and U should not include 0, right? Otherwise, you're not going to be able to find a branch of the logarithm. And actually, you can't find a branch of the logarithm in any old U, even if it doesn't include 0. It had better be special in some way. Maybe the slit plane, but it could be other things. It could be some disk that doesn't include 0, right? There's lots of different, any star-like set that doesn't include 0 will, we will have an antiderivative of 1 over z in it, right? But there's other, other types of U. There's lots of other domains where we can define an antiderivative of 1 over z, an actual function, not a multivalued function, but an actual function, right? So that's what a branch is. Right, so, and we follow a branch, right, we start at a point, right? We, we pick some neighborhood. We define it has to be small enough so that there's some branch of the log defined in it, and given a small enough neighborhood, you can pick a small enough star-like neighborhood, like a disk of any point, and you will get, as long as it doesn't include 0, because that's where 1 over z is not defined, you can get an antiderivative. So as long as it's a small enough neighborhood so that we can find an antiderivative, where we can find a branch of the logarithm. So we take it, we defined it in a small neighborhood, and we're following it along a path. Well, at some point we're going to get out of our neighborhood, right? So we maybe pick another neighborhood where we define our chart. I'm going to actually have a picture out here. So we change to another neighborhood and just make sure it's equal at a point. So here's the and etc. You keep going. So here's the picture. So we define our branch over here, right? Then we want to keep going along this path, right? So we get to, let's say, this point, right? And then we define, we get a new neighborhood where a branch is defined, but where we can go a little further along our path. And we pick the branch of the logarithm in this new neighborhood that is equal to the old branch at this point, right? And then we keep going, right? We get up to here, and now we were going to go out of this neighborhood. So we pick a new neighborhood where we can go a little further. We make sure that our branches are equal at this point, and then we keep going, right? So this is what you do when you're following a branch. Now, in this picture, it seems like, well, we could just pick a branch that just works everywhere here. Yes, but in a more complicated path, for example, the circle, right? It's the least complicated path where you can't just pick one branch. As you're doing this, at some point, you're gonna you're going to have to run out of your neighborhood, right? Any neighborhood where a branch exists is not going to include the entire circle, right? So you're going to have to use at least two neighborhoods, right? But really, if we're looking at the, let me, go back to the graph, right? I mean, I just need to think, well, near here, and I don't really have to sort of think about a specific neighborhood, right? But I know, or near here it has these values, then near here it has these values, near here it has these values, and so on, and I keep going, and I end up here, right? And I could look at sort of a sequence of maybe disks, right, that keep going around. Or I can use, in this case, I could use slit planes. I don't have to use disks. Disks will work, right? I would just have to use more disks. Slit planes, I would have to use two. I would be, I could go around once. The circle is two slit planes. It doesn't really matter what neighborhoods I use. But, you think of moving along this locally, right? You go always a little bit further, and you go around the entire path. All right. So, and that's what we did. All right. So, so that's it for definition of the logarithm. It was maybe this lecture was a little bit hand wavy, but it sort of tells you what the logarithm is. That was not hand wavy. That's the actual definition. That's the precise definition. But how it's used maybe was a little bit hand wavy. But it's this sort of idea, right? And we'll see this idea, a few more times, right? So this is how one can do it. And if you want to use if you want to be completely precise with doing this, what you could do is you could cut up your path into little pieces where where you have a well-defined branch, and then you can use the fundamental theorem of calculus in the actual, like without the quotation marks, right? You can use the actual fundamental theorem of calculus, and you just have to compute this with a bunch of applications of fundamental theorem of calculus, right? So that would be the completely precise way of computing with the logarithm, right? You have to figure out what those branches are, right? But in the end, I mean, all you're doing is following the graph as we did, right? So that's just being completely rigorous about it. All right, so next time what we're going to do is we're going to look at winding numbers. So that's sorry. So that's numbers that tell you how many times you go around a point, because computing those is actually one of the things that allows us to compute lots of strange integrals, and actually something that allows us to compute a whole bunch of things. Just knowing how many times does a path run around a point in either this or that direction, and that's easy to tell even just visually, right? I can just look at it. The circle goes around once around the origin in the positive direction. I can just glance at it and know that, and actually it's going to give us, we're going to be able to compute integrals. We're going to be able to find zeros of functions and find singularities of functions and all sorts of stuff by this idea. So this winding numbers, that's what we're going to look at next time. Actually, it's sort of it is also a little bit of a not an introduction, but a little bit of a foray into topology. Topology comes into it because we are counting counting going around points or going around holes, or and that gives us some. We're going to basically compute certain topological groups, or one group of sets in the plane, right? Okay, so that's next time, and it's not going to be as complicated as I've made it, but it's all right. So see you then.